Hello, guys. John the Quant here. I was reading an article the other day, and it was about applying Bayesian methods to A/B testing. And definitely, it allows us to draw different kinds of conclusions, and especially to word those conclusions differently. It was pretty fascinating, so I thought that's what we would talk about today. And no, this means we're not going to be doing finance, but that's okay. First off, what exactly is A/B testing? Well, the term is typically used in user experience design or analysis, but statistically, it's exactly the same. It's really just a two-sample hypothesis test. It'll have a single independent variable, and it's among hypothesis tests, it's really one of the more simple kinds. It's not too hard. We're all going to be fine. When might you use it? Well, our pretend scenario is going to be a fitness blog. And this blog is going to have one of those pop-ups where you type in your email address and you join their mailing list. And what we want to know is what picture should we put in as part of that pop-up. We've got two options. There's going to be one with the trainer, standing there with his arms crossed and smiling at the camera. And that's very nice. And there's going to be another one where he's going to be showing off his muscles. And I can understand how that would be alluring to some people. But which one is going to get more people to sign up? And that's where this A/B testing comes into play. So really what we're going to do is we're going to run through first our pretend scenario where we already know the answer. We're going to be making up the data so we know exactly what the answer ought to be. Then we're going to do a simple application of exactly the same methodology, but in a non-user experience context. And then we're going to look at a couple of ways to make it a bit more interesting. We'll do a linear regression model, and we'll also do a logistic regression model. And both of those are going to have more than one independent variable. Shouldn't be too hard. Should be pretty interesting. We're going to be working in Colab today, so let's just go over to the computer and try it out. All right, here we are in Colab. Your Colab generally, we're going to use SciPy for the traditional hypothesis tests, and you've got to upgrade SciPy inside of Colab before you can use the function that we're going to use. You might have to restart the runtime after, but it's not a big deal. We'll be using PyMC3 for our Bayesian sampling. We'll need NumPy, and of course we're going to use this t-test, this two-sample t-test function from SciPy for traditional hypothesis testing. Again, our scenario is we've got a fitness blog that's got a pop-up trying to get people to sign up for the mailing list. We have two possible pictures to put in the pop-up. One is going to be the trainer with his arms crossed and smiling, and the other one's going to be the trainer showing off his muscles. And we want to know which one is going to get more people to sign up for the mailing list. And we're going to use Bayesian A/B testing for that. So once we've imported our libraries, we're creating the data ourselves. We'll set the seed, and then each one of these, this is the smiling observations. So for the next 10,000 visitors to this fitness blog, we're going to split them about 50-50, and half of them are going to get a pop-up that's got a picture of the guy smiling, and half of them are going to get a picture of the guy showing off his muscles. And we're going to keep track of the proportion of visitors that sign up after seeing each of the two pictures. So that's what we're saying here. We've got a binomial draw, and the probability of success, the probability that someone signs up seeing the smiling picture is going to be 1%. Probability of someone signing up seeing the muscle picture is going to be 1.2%. So we know, because we're making this up as we go, that the muscle picture is better, and we want a hypothesis test to tell us that. Slightly better. So let's see what the actual conversion rates that we got from our random sample. About 9, a little less than 1%, a little less than 1.2%. So we're kind of underestimating the true values here, which is good because in real life, they're never going to tell you the actual values. You're going to get something close, but not exact. This next line runs the traditional A/B test and gives us a p-value of 42%, so 0.42, very high p-value, and it really means that we can't tell if there's a difference. Our alternative, being two-sided, means we're just saying, is there a difference in the number of people that sign up based on the two pictures? And this p-value says, statistically, not really. So let's try the Bayesian method, see if we can get more information. This is how we're going to set up the model in using PyMC3. We'll say with pm.model, and then we'll need to give a prior distribution to each of the conversion rates. And we'll be using beta distributions because they're very flexible, and our smiling conversion rate and muscle conversion rate are going to be the same. We can see our parameters being 1 and 99, and this is going to give us a very steep beta distribution where almost all of the probability is really low. It's really close to 0, which is what we want because we know that it's about 1%. Then our observations are going to be Bernoulli random variables. The probability of success will be sampled from this prior distribution, and then we've got our observations. And this trace part just tells everything to PyMC3 to just sample everything and keep track of what we need it to keep track of. These can take a while, so I am going to speed up the sampling parts in post-production. All right, we've sampled 2 chains for, it says 1,000 tuning observations and 1,000 drawing observations. This one didn't take very long either. Let's go ahead and look at the posterior distributions for our conversion rates. As we can see, our mean rates for each one were about what we saw from our observations, which is excellent. That's exactly what you want. And here we said it goes from about 0.7% to about 1.2%, and the muscle conversion rate goes from about 0.8% to 1.4%. And we can tell there's pretty significant overlap between the two, which explains why we got such a high p-value. So traditionally, in traditional hypothesis testing, we couldn't really say much about the difference, but in Bayesian hypothesis testing, we can. And how we're going to draw those conclusions is we're going to look at the posterior. We're going to get our posterior samples for the smiling rate and the muscles rate, and we're going to look at how often is the conversion rate for the muscle picture higher than the conversion rate for the smiling picture. And that's going to tell us the probability that the muscle picture is better at driving conversions than the smiling picture. We get 78.5%. So in a usefulness kind of context, this p-value says we can't really tell the difference between them. And this one says maybe we can't tell the difference between them, but it is pretty likely that the muscle picture is better. So imagine you are a fitness blogger and you've hired some, UX designer or something to help drive conversions. You want more people to sign up for your mailing list. So if they just come back and they say, well, this p-value of 0.42 says that there's no difference between the pictures, do whatever you want, that's not very helpful. But if they can come back and say that the probability that the muscle picture is better than the smiling picture is 78.5%, so just to err on the safe side, go ahead and use the muscle picture. That's something you can easily act upon. It delivers a lot more value to the client that way. So that's what really makes Bayesian A/B testing useful, is being able to do this part right here at the end. So let's try a real data scenario. We'll import pandas, and this data set that I've got here, I know it's from Kaggle, but I don't remember exactly where I've got it. It's about cancer survival. So we've got all these different variables, but what we're really interested in, at least for now, is going to be this one, urban versus rural patients, and whether or not they survived for a year. So the question we're going to ask is there a difference in survival rates between urban and rural cancer patients? So we're going to pull out those two columns that we care about, and we're just going to have to make sure that the rural and urban column is pretty clean. And it is. So we'll just move on. We're going to change it to a binary column, ones and zeros, 1 for urban, 0 for rural. We'll pull the urban and rural observations out and see what we've got. Let's see, there's about 7,600 urban patients and over 17,000 rural patients. And what this is really going to mean for our Bayesian hypothesis test is that the urban survival rate is going to be more spread out. We're going to have a wider range of possibilities for that one. Now let's do a traditional hypothesis test. Again, this is a two-sided test, so we're really just saying, Is there a difference in survival rates between urban and rural patients? And our p-value is 0, which means, yeah, there is. Statistically, there is very likely to be a difference between the survival rates of urban and rural patients. It doesn't really tell us what that difference is, but it tells us that there is a difference. Now, I want you to notice here, before we run this one, that it is exactly the same setup as before. We're starting with an urban rate and a rural rate. They're both beta distributions. We kind of flattened these out rather than just making all of the probability be, close to 0. We're flattening it out quite a bit so that it can go wherever it needs to. Then we're treating the observations as Bernoulli random variables, with the p-value coming from the prior there. And we've got our observations. We'll do all the sampling, and again, we'll speed this up. All right, let's go ahead and plot the posteriors here. We can see our mean and, our mean for both the urban rate and the rural rate. I guess we didn't print that. Oh, here it is. 54.7, or about 0.55 there, and 67.2, or about 0.67 here. So those means are good. And for the survival rates, we can see that the urban rate is probably somewhere between 0.54 and 0.56, and the rural rate is between 0.67 and 0.68. So there's no overlap here at all, which is why we got such a low p-value from the traditional method. But again, Bayesian A/B testing lets us say this sentence: the probability that rural patients survive at a higher rate than urban patients is 100%. From this data, we 100% are certain that rural patients survive more than urban patients. Let's move on. Let's try something a little more interesting. We'll do it with multiple factors now. And our second factor, if we go back up here, now we care about urban and rural, but we also care about smoker or non-smoker. Just from what we know about smoking, it seems highly likely that smokers will survive less than non-smokers, but let's find out. So we're going to grab those 3 columns that we care about, and we're going to check to see if the smoker column is clean, and it is not. So what we're going to need to do is take all these different versions of no and change them to be the same thing, all these different versions of yes to be the same thing, and then these ones where they don't say, we're just going to throw those out because they're not helpful to what we want to know. This batch right here, this cell, it just kind of cleans everything up, and then it creates binary columns for everything, and I'll show you. There, so it's cleaned up. We've got 0 for non-smoker and 1 for smoker, 1 for urban, 0 for rural. Then I actually segmented it out. We've got urban non-smoker, so these are people who, urban smoker, so this will be people who smoke and live in the city. Urban non-smoker, people who live in the city but don't smoke. And rural smoker, people that don't live in the city but do smoke. And then notice we have 4 combinations but only 3 groups here, because 0, 0 takes care of the rural non-smokers. So we really only need to care about these 3 groups. If we try to put a 4th group in there, we'll have problems. This is how we're going to set this linear regression model up. This is really a linear probability model because y is 0 or 1, so really we're predicting the probability of survival. So alpha will be our intercept, and alpha is going to take care of those rural non-smokers. They're going to be included in that intercept. Then we'll have a coefficient for urban smokers, a coefficient for urban non-smokers, and a coefficient for rural smokers. So these 3 coefficients, what they're really telling us is a comparison between the group that the person falls into and the baseline group, which is rural non-smokers. Slightly different PyMC3 model here. Started off the same way. We need to set up priors for each of our coefficients or each of our variables here in the linear regression. So that's alpha. I just set them all up as normal distributions with mean 1 and standard deviation, mean 0, sorry, and standard deviation 1. alpha, beta 1, beta 2, beta 3, and sigma here is going to be the variance of this guy. This little bit on the end of a linear regression always has mean 0. It's always normally distributed with mean 0. So we really just need to make draws for the standard deviation. So I used the half normal distribution from 0 to infinity because its standard deviation has to be positive, and gave it a standard deviation of 1. The expected value for this regression is going to be you add up all of these things and just leave off the random epsilon bit at the end. So our mu is alpha plus beta 1 times urban smoker plus beta 2 times urban non-smoker plus beta 3 times rural smoker. Leave this bit off. And then we'll say that y, which is our probability, we're going to have it follow a normal distribution, and its mean is going to be the expected value, and its standard deviation is going to be the standard deviation of that epsilon. And then what we observed is the survived column. And we'll just draw samples from all that. This one is a bit more complicated, so it does take a bit longer. All right, that's done. We're going to plot the trace of that, and I'll tell you what we're looking at in this trace. So what we're looking for is, we said that these all followed, normal or half normal distributions. So we're looking for something that looks pretty normal. And we want the solid line and the dotted line to be very close together. This indicates that the two chains that we sampled have converged. And we want this to look like white noise. We want it to look really random, not any kind of relationship between one value and another value. And this all looks pretty good. We're going to look at a table for a table of kind of the statistical stuff. We'll talk about what it means. We've got our means for each of the coefficients. You can see that alpha, the mean of alpha is about 0.756 down here. And that's pretty good. That means rural non-smokers, in general, the survivability is pretty high. It's about 75% survival rate. That's pretty great. But you can see that all of our betas are negative, which tells us that being in any other group from rural non-smokers is bad. Being an urban smoker means you're less likely to survive. Being an urban non-smoker means you're less likely to survive. And being a rural smoker means you're less likely to survive. We can look at our confidence intervals here for these. This is a 94% confidence interval, and 0 does not appear in any of these, so that would indicate a p-value being quite low in a traditional setting. And really important here, we need to look at the effective sample size. What we really want us to see is that these numbers are pretty close together. Really big differences kind of indicate that you had some divergence problems. And r hat close to 1. R hat close to 1 is probably the most important thing in this entire table. If r hat is far from 1, that means that your chains did not converge and there's some kind of problem either in your model or in how long you sampled for. Our worst one is for beta 3, which is interesting because beta 3 seems okay to me. But again, this is pretty close to 1, so we don't need to worry about it. So what we're going to look at right now is the probability that each coefficient is positive. So what does that mean? The probability that each coefficient is positive is the same as the probability that each group survives more than rural non-smokers. That's what it says right here, but that's also what it means. That's what we talked about when we said that alpha includes rural non-smokers, and each of these beta coefficients is a comparison of these other groups to that alpha group. And it's all 0. So definitely urban smokers survive less than rural non-smokers. Definitely urban non-smokers survive worse than rural smokers, and definitely rural non-smokers survive more than rural smokers. Okay, so rural non-smokers 100% have the highest survival rate of all 4 groups. We can actually do the same analysis in a different way. Here we split them up into 4 groups. 4 possible groups. But PyMC3 actually just lets you use a formula, okay, like you would in R if any of you guys have used R before. So this is just saying our formula is survived 1 year, okay, is our independent variable. Smoker is an independent variable. Urban is an independent variable. And we're using the interaction between the smoker and urban columns. And without any other inputs, this is going to return a linear model structured very similarly to the one we used before. We'll let it run. It'll take a few minutes. All right, we're all done. Let's go ahead and plot the trace like we did before. Yeah, there we go. And as we can see, again, this looks very much like white noise, very random, and everything seems to have converged pretty well. The possible problem in this standard deviation one. But let's look at that table and see what the R hat values say. All of our R hats are much closer to 1. That's excellent. We see a little bit of difference in the effective sample sizes, but it's not that bad. This is definitely the worst difference, kind of explains why we might have that bit of divergent looking behavior in this graph right here. These are close to 0, which is great. Mean, again, we got 0.756. That's excellent. That still includes the urban, the rural non-smokers. It says smoking makes you less likely to survive. Being urban makes you less likely to survive. And the combination of smoking and urban living is also bad. And again, our, what are they called? Confidence intervals. Sheesh. The confidence intervals don't include 0, so that would kind of indicate that in a traditional setting, we would have gotten p-values that were very low. And speaking of a traditional hypothesis test, let's go ahead and run one. We'll get a linear regression table and then our traditional Anova. So the Anova down here tells us that smoking does make a difference, urban living does make a difference in survival rates, and the interaction between smoking and urban living also makes a difference in survival rates. All these p-values are very, very low. Now, the Anova table tells us there is a difference, but not what that difference is. So that's why we need the regression table, where we have that smoking has a negative coefficient, as does urban, as does the interaction, which tells us that each one of those makes you less likely to survive than being a rural non-smoker. Okay, so we got these same conclusions. We just get a little more information about them. It does take longer, but we do get more information using the Bayesian methods. Now that was a linear probability model, which you may not actually end up using. A lot of times when you have a binary dependent variable, you would probably use logistic regression instead. And this is very easy in PyMC3 as well. We start off the same way. And from formula, we've got survived 1 year as the dependent variable, smoker, urban, and the interaction as independent variables. But now we just need to say family equals binomial. And that's going to change from the linear probability model from before to a logistic regression model. This time I had to turn up the tuning. So instead of having 1,000 tuning draws from each one, I changed it to 2,000 because I was running into some issues with the R-hat stuff. So let's run this and be back in a second. Okay, finally, that one took a while. 493 seconds. What is that in minutes? Anybody know? 8 something? Whatever. Let's go ahead and plot the trace now. All right, yeah, this all looks pretty random. Everything seems to have converged really well, and that's partly because we had a large sample size and partly because we used more tuning steps. Large sample size, a lot of sampling draws, a lot of sample iterations. Let's go and look at that table. R-hat's all very close to 1, that's great. A little bit of difference in the effective sample sizes, but nothing very big. These are close to 0. Good, good, good. So our intercept, these are much more complicated to understand than in the linear model. Just know that some of them are positive and negative. So negative means it lowers the probability of survival. That's the easiest way to interpret this. Negative lowers the probability of survival. So smoking definitely lowers the probability of survival. Being urban lowers the probability of survival, and that interaction also lowers the probability of survival. For this one, we're going to look at some more plots. So we'll use matplotlib and Seaborn here. In these two lines, we're just drawing all of those samples out of the two chains of the posterior, and then we're just going to plot them together. We'll talk about what this plot means. So what we're looking for here, these are the samples of all of the coefficients. And we can see the distribution of the coefficients again, same as it was up here. But what we're really interested in is there a relationship between them? And these both kind of just appear like a big dot. So really there isn't much of a relationship between them, which is what we want. If there was a relationship between the two coefficients, then it is likely that we left information in the data. We didn't get it all out. So this is good. Here we're just pulling out the rest of the posterior draws from each chain. Then we're not going to use all of them. We're going to get the actual probabilities, but there's, I don't know, millions of draws altogether, millions of combinations. We're not going to use all of them. We're putting string labels on those. So we'll set everybody to rural non-smoker, but then those that are urban but not smokers will change to urban non-smoker. Those that are not urban but do smoke will change to rural smokers. Those who are urban and smoke, we're going to say are urban smokers. And from this point, I'm going to speed this up a little bit so you don't have to wait around for everything to run. I messed up. Sorry guys, I found some mistakes, so I went back and changed them. I'm not sure if I left it out of the video entirely or if I moved it back in, but I may have just fast forwarded through everything so you get a nice time lapse of me correcting myself. There we go, finally. All right. This is what we were looking for the whole time. This is the final distribution of the probability of survival for each group. You can see rural non-smokers have a very, very high peak, and it is also furthest to the right, meaning they've got the highest probability of survival and the most consistent probability, and it's probably about 0.75, which is what we've been estimating this whole time. We can see urban non-smokers are next. They're a bit more spread out, but they're pretty survivable. We've got rural smokers, and then way down here, urban smokers being by far the least likely to survive. In fact, they're the only group that has less than 50% probability of survival. There we go. That's all of our examples of what I called Bayesian A/B testing, and I know most of it wasn't A/B testing, but it was all hypothesis testing, and it was all Bayesian inference. So just, let me know if I messed anything up. I know I messed up the programming, but I could have messed up the conclusions or the math or the modeling or any part of it. And I would really like for you guys to share that kind of insight with me. And let me know where you think this kind of Bayesian inference would be useful. And I know PyMC3 makes Bayesian modeling very, very simple. So go ahead and give that a try. There's plenty of documentation on it as well. I'll link to that in the description. And feel free to like and subscribe. Do whatever you want. And I'll see you next time. Thanks.